Hey everyone, welcome to the 8th lecture in our series on imitation learning. I'm Sanjiban Chaudhary, a research scientist at Aurora and soon to be assistant professor at Cornell. Today, we'll look at imitation learning as simply a distribution matching problem. That is, generate trajectories that look like that of the expert demonstrator. Now, at the heart of the problem lies a question. What is the measure of closeness that we should use? That is, the divergence between two distributions. At the end of the lecture, we will have a clear answer to this question, but we need to build up to it. So, what better place to start than with an example? Let's consider a new application, autonomous drone flight. So you've decided to enter an autonomous drone flying competition where you have to take an RC glider, make it autonomous, and make it fly through forest canopies. Now, being the imitation learning experts you all are, you have decided to hire an expert RC pilot that provides you demonstrations of how to fly fast in forests. Now, if you look at the spread of expert trajectories, notice how they spread out really wide in open spaces, but then constrict as they're flying in between tree corridors. And that is precisely the behavior you would want out of your learner, to sort of constrict as it's flying through trees and spread out when it doesn't need to. Turns out we can formalize this desiderata by framing imitation learning as a distribution matching problem. So, as always, let's begin by writing down the MTP. Here we have only state, action, and transition function. Note, we're going to omit cost function from this discussion for now. Now, given an MDP, we can define a policy as a mapping from state to a distribution over actions. So that's essentially what we are trying to learn. When we execute a policy, we get a trajectory, which is a sequence of states and actions. So a policy induces a distribution over trajectories. Think of it as a joint distribution over state and actions across all time steps, which, because we're in an MDP, we can efficiently write down as a product of the initial state distribution times the policy times transition and so on. Finally, we assume that the expert 2 is a policy, simply that this policy is unknown to us. And as a result, the expert also induces a distribution over trajectories, which is unknown since the policy is unknown. All right, so what is our goal? Our goal is to match the learner and expert trajectory distributions. We can formalize this mathematically as solving an optimization, where we are solving for policy pi that minimizes divergence delta between the learner distribution p pi tau and the expert distribution p pi star tau. Now, before we can proceed any further, right off the bat, we run into two main problems. First, which divergence delta should we use? Changing delta affects the nature of the optimization problem, so that's important to figure out. Two, pi star is unknown. All we get are samples from p pi star tau. So how can we compute delta exactly if all we have are samples? So you notice there's an asymmetry at the heart of things, right? On the one hand, we have pi that we are solving for, so we know everything about it. On the other hand, we have pi star that is latent, and all we see are samples. This means that delta cannot be computed exactly, and instead we must build an estimator. Okay, so let's tackle these problems one by one and begin with the first problem, the question of what divergence to pick. Now, a natural choice is to pick a popular divergence in machine learning today, the Kullback-Leibler or KL divergence. A forward KL, simply put, is the expected log density ratio, where the expectation is taken with respect to the expert distribution and the density ratio is expert over learner. You might be wondering, what does this divergence actually capture? We're going to use a simple example where the glider is faced with a tree and 50% of the demonstrations go to the left and 50% go to the right. So what policy would we learn if we minimized delta KL? To see this, let's go back to the math and expand out terms and drop terms that don't depend on pi. So we can write the optimization as min pi. Now we are going to plug in the formula for trajectory distribution. If you recall, that was simply probability of the first state times a policy times a transition function and so on. So you're going to expand that in both numerator and denominator. And you should notice that there are terms in common that we can simply cancel out. So we're left with expectation of log of product over density ratios of the expert policy over learner policy. Now, notice that we can write log of a product as sum over logs, right? And once we've written that, we can actually go ahead and drop the numerator since it doesn't depend on pi and simply keep the denominator. Okay, now we can pull both the negative sign and the sum over t equal to 1 to t all the way to the outside and simply rewrite the inside term as an expectation where state and actions are drawn from the expert distribution times log pi of the expert actions. In other words, this is the log likelihood of the expert actions under the learner distribution. Now this expression should be familiar to you all. This is behavior cloning. You're simply minimizing the negative log likelihood of the expert actions on states visited by the expert. We suspect what can go wrong with behavior cloning, as we've seen in lecture 2 and lecture 1, but let's do the exercise anyways. So let's look at our example where we have a bimodal expert, because the expert goes with some probability to the left of the tree and with some probability to the right of the tree. So you have two bumps. Now what would forward KL do? Because it's kind of minimizing the negative log likelihood, it'll try to cover the two bumps. So you're going to see this sort of red line that tries to cover both bumps. You can only imagine what happens when you execute this policy. You get the spray of trajectories, a bulk of which just rams straight into the tree. And in some sense, we should expect this because the loss does not disincentivize this, right? It asks the learner to say that for any action that the expert can pick, make sure you put some probability mass on that action so the loss doesn't become infinite. And as a result, there's nothing saying don't put any probability mass where the expert does not pick any actions. Now, as we say this out loud, it seems that we can take this argument and flip it around. In other words, if forward KL forces the learner to cover the expert, can we simply reverse the direction? Can we say the expert should cover the learner? In other words, reverse the order of arguments in the KL divergence. What would that even look like? Going back to our original problem, that would force the learner to put all of its probability mass within the expert support. In other words, it's not allowed to pick an action that the expert does not have a non-zero probability of selecting. By the way, because scale is asymmetric, we use the word divergence and not distance when we're thinking of the objective function, because distance is traditionally a symmetric metric. Okay, so back to our problem. We can write out the reverse scale expression as, again, expectation of the log density ratio, where the expectation is taken with respect to the learner distribution and the density ratio is learner over expert. Just like we did previously, we can expand out this term, again, split up the trajectory distribution as product of individual distribution, cancel out common terms, and we get the familiar log of sum over log of density ratios between learner and expert. Now this time we cannot remove any terms because everything depends on pi. The key bit here is that the trajectories are themselves drawn from the learner distribution. Okay, so the first term in the expression can be thought of simply as the entropy of the policy on states visited by the policy. This term incentivizes pi to be as sort of spread out as possible. The second term is interesting. That's the log likelihood of actions chosen by the learner measured under the expert's likelihood function. So log pi h of at given st. What does this do in our example? Well, just like before, this says for any action that the learner picks, if the expert policy pi h assigns a 0 probability to that action, the term blows up. Log of 0 is, of course, a negative infinity, so your objective function blows up to positive infinity. And this is the mechanism that keeps the learner locked into the expert support. But there's a problem. Have you noticed it yet? We actually don't know the distribution pi of h. It's unknown. If it's unknown, how can we ever evaluate it? If you can't evaluate it, we fundamentally cannot compute reverse KL. This was problem 2 in our list of problems. We don't actually know the expert distribution. All we have is samples. And hence a natural question to ask is, can we build an estimator using these samples? And in a wonderful paper, Nguyen et al. Showed that the answer is yes, we can build such an estimator. More surprisingly, not just for reverse KL, but potentially for any divergence belonging to a larger family. So a bit of an aside, KL divergence, reverse KL divergence are instances of one big family of divergences known as f-divergence. The way it goes is delta f between p and q is expectation of f of the density ratio between p and q measured with respect to q, where f is any convex function. So let's say you wanted to get forward KL. Simply observe that by setting f of u is the density ratio here, as log of u, you get the forward KL divergence, right? So that's interesting. What about reverse KL? For reverse KL, if you set f of u as u times log of u, you end up getting reverse KL by canceling out q of x. And if you're interested in how to get more divergences, I would recommend reading the paper that has a whole table in it. Okay, so how do we build an estimator for f-divergence? Well, there's one simple trick we're going to use. We're going to use the variational form of f of u. What is a variational form? You can write f of u as sup t belongs to the real number space, t of u minus f star of u, where f star of u is the convex conjugate of f of u. This is simply the definition of convex conjugate. So you could have also written it as f star of u is equal to sub t belongs to r, t of u minus f of u, and that is in fact the definition of convex conjugate. So the conjugate of a conjugate is the original function. Now why do we care about this form? Well, bear with me. If you plug this form back into the original expression for f-divergence, you get delta f between p and q is expectation with respect to q of x. Plug in the expression. So you get sup t belongs to r, t times u is the ratio p of x over q of x minus f star of t. Now, the trick is to pull the sup outside of the summation. Now, when you do that, t is no longer going to be a constant but dependent on x. So we're going to replace t with phi of x. So the expression becomes sup over phi of x, expectation with respect to q of x, times phi of x times the density ratio minus the convex conjugate of f. Now notice that because we pull the sup out, we get a lower bound by Jensen's. Now, this trick gives us an estimator. Why? Notice that this expression is entirely linear in P of x and Q of x, which means we can estimate it simply by having samples from P of x and Q of x. We don't. So in a nutshell, the variational form allows us to take the distribution P of x and Q of x that were locked inside this sort of nonlinear function f and make it linear in P of x and Q of x, allowing us to estimate it from samples only, which is a pretty cool trick. Okay, so what are these phi of x functions? I want you to think of these as the moment functions that we described in lecture 6. In that case, the first expression is simply the moments of phi of x when measured on P of x. The second function is the moments of f star of phi of x measured on Q of x. And everything in this expression can be evaluated with just samples from P of x and Q of x. So we have a legitimate estimator. Now, does this remind you something familiar? Something that you've seen in previous lectures? Notice if you have a sup and a min, surely there is an underlying game going on. And indeed, we can think of f-divergence minimization as a game, a point made eloquently in a paper by Nguyen et al. Called FGAN, which I highly recommend reading. Two players, a generator that's generating distribution P of x, and a discriminator that's choosing moment functions phi of x. The payoff score is difference between expected moment evaluated on P of x and f star of the moment evaluated on Q of x. It's just an asymmetric moment on P of x and Q of x. You can think of the first term as the learner score and the second term as the expert score. Okay, so can we apply this framework to imitation learning? The answer is yes. So in a paper by myself, along with collaborators, we showed that imitation learning can indeed be expressed as f-divergence minimization. So how does this work? So player 1 here is a policy pi. Think of that as a generator. And player 2 is a function phi that maps a trajectory tau to a number. Think of this as a cost of a trajectory. The payoff function is the same, cost of the learner trajectory minus a modified cost of the expert trajectory. As we mentioned, if we view phi of tau as cost of a trajectory, we can always choose a representation that says cost of a trajectory is sum over per time step cost, right? So we can plug this back into the game, and this time our second player is simply choosing one-step cost functions that kind of makes the learner look more expensive while making the expert look cheaper. Now, the only caveat is that the expert's cost goes through the function f star, the convex conjugate function, which is going to play a big role. Okay, so the way we solve this game is we are trying to find a minimally discriminative cost that separates learner from experts, and then the learner goes and minimizes this cost. All right, so let's see how this plays a role in estimating reverse KL. So recall earlier that for reverse KL, f of u is simply u log u. And if you take me on faith that the convex conjugate of this function is x of u minus 1, you can derive this by writing out the expression of convex conjugate and then setting the gradient to 0. Okay, so let's bring back our favorite example of flying either left or right around the tree. Let's see what the f-divergence game gives us, right? So we are minimizing pi, maximizing cost functions. The payoff is cost of the learner minus the cost of the expert pushed through an exponential map. Well, let's pause here. The implications of this asymmetric cost is going to give us the behavior we want. To see this better, think of things from the perspective of the adversary. The adversary wants to make the learner look way more expensive than the expert. The only way it can do that is by making any state that the expert doesn't visit exponentially high and make the states that the expert visits as close to 0 as possible. Now, in other words, the adversary puts all the cost mass precisely outside of the expert support. So you can see this by the purple shadings. And it's like a force field that keeps the learner locked in inside the expert support. As long as the learner is inside the expert support, it pays no cost. And as a result, it's never incentivized to leave the expert support. So you see trajectories either going to the left of the tree or to the right of the tree, never in the middle and never on the sides. Okay, so to summarize, the intuition was to penalize exponentially more states that the expert doesn't visit. So penalize for leaving the expert support, which is exactly what we want out of our reverse scale minimizer. The cool thing is this idea can be extended to a whole host of other divergence. For example, you might be saying, well, what about, can I have a symmetric version of KL? The answer is yeah, you can choose something known as the Jensen-Shannon divergence, typically used in GANs. And the Jensen-Shannon divergence is essentially the distance, the reverse scale distance from P to the midpoint between P and Q, as well as from Q to the midpoint between P and Q. So it's completely symmetric. You can switch P and Q and you get the same answer. And if you plug this back in, if you compute F, which looks a little complicated, and F star of U, and do a little bit of algebra, you end up deriving the loss function for a typical GAN. And in fact, there's a paper called Gale that exploits this to compute policies that minimize J's divergences. So this segues well to our last and final question. There's so many divergences to choose from. Which one should we minimize? To answer this question, let's try to list down a set of desideratas. So first, the estimator that we are building should not be an approximation, but should be exact. Unfortunately, the f-divergence estimators are all lower bound approximations, as we saw earlier. So they're not exact. So there may be a gap between the estimate and the exact divergence. Second is that the estimator must be sample efficient. So fortunately, the reverse scale estimator, because it has a exponential term in there, it needs exponential number of samples to accurately estimate. Number three, the estimator must be correlated with the final performance. In other words, the moment functions that we are using must have some relation to the actual cost functions that the human might care about. And to see a concrete example of this, let's consider the glider example where we are flying through trees. And let's say there's a patch of clouds. And you collect demonstrations from the human flying, and you see that while they're while the trajectories concentrate to pass through the narrow gap between the trees, doesn't seem to care a lot about how it behaves near clouds, right? And so this is intuition we have that one moment function that we really might care about is to sort of match the distance from trees, right? But if we come up with a second moment function, for example, match distance from clouds, we wouldn't really care about the second cost function. I can't imagine that having any impact on performance. So put differently, the moments we're using in our estimator must ultimately relate to the moments of the human's cost function. And it turns out there is a class of divergences that do in fact meet all three of our desideratas. They're called integral probability metrics, or IPMs for short. There's a wonderful paper on IPM I highly recommend reading, but to put it compactly, IPMs are by definition difference in expected moments measured of P of x minus Q of x, where the moment is the maximum moment function from a class of moment functions. So it's a lot like the estimator we've been looking at, but this is directly the definition of IPM. It's not an estimate. The wonderful thing about IPM is it's linear in F, right? It's sample efficient to estimate, and it's not an approximation. It's the exact metric, which was the first thing we wanted in our desiderata. Okay, so an example of IPM is total variation metric. It's pretty popular, where the class of functions has the L infinity norm bounded by 1. Another class of IPMs is Wasserstein distance. So, for example, Wasserstein-Ganz use this is an example of an IPM metric where the Lipschitz norm of a function is bounded by 1. Finally, MMD, mean max divergence, is a third example where the RKHS norm of a function is bounded, right? So the only parameter in IPM is your choice of functions. And IPMs in imitation learning has this really natural connection. So you can think of an IPM as, again, pick the maximum function in your moment class and then measure the expectation of this function on the learner distribution minus expectation of the function on the expert distribution. And moreover, this function is a sum over one-step function evaluations. So it looks a lot like a cost function, right? Sum over cost of the learner minus sum over cost of the expert. So only one question remains. How do you pick the class f? If you look at the expression, it suggests to pick a class f of moments of the cost function, right? Because the expression says cost of learner minus cost of expert. That's what you want to minimize. And so IPMs has this intuitive connection to the policy performance. To understand better, let's look at an example where we are doing imitation learning from observations alone. So you have a humanoid robot and you want to imitate Olympic gold medal winner Simone Biles. Now, since Simone is not a robot, she can't actually tell you the actions she executes when she's doing a move. Instead, all you really have is a sequence of states. Here, states are the various configurations that she goes through when performing a move, right? And imagine we can use computer vision to extract her state at any given point of time. So we have a sequence of states. We also have a set of cost moments, F1, F2, all the way to Fk. These cost moments map state to a number. That's a description of how good that state might be, right? So what is the rotational speed of a state? Or how much height does that state achieve? Is the state a tucking configuration, and so on? We will now talk about an algorithm called forward adversarial IL, short form of FAIL, by Sonadal, that uses IPM to imitate from observations alone and does so efficiently. Right, so the algorithm is very intuitive, hence we'll be able to walk through it fairly quickly. So the algorithm iterates over every time step from 1 to t, and we're going to learn a policy for each time step, right? So first, think about the states that Simone visits as shown in blue, right? We don't know the actions she took, but we have the states. For every time step, we're going to roll in the learner to get to the state at that time. And then we're going to try out every single actions to see where we get to the next time step. So let's start from t equal to 0. We're going to try out every single action, right, to get all possible future states. We will then solve a policy by minimizing the IPM metric, right? So we are trying to find a policy that picks an action that takes you to a next state that's as close to the demonstrated state as possible. And you keep repeating this. So again, the next time, so pick an action that takes you as close to the state, and so on, right? And every time we are solving for this policy, we are first finding the maximum moment f, that distinguishing between learner and expert, and then we are updating the policy, right? And at the end of t rounds, we have a policy for every time step. So this algorithm reduces imitation learning to a simple classification problem that we can solve efficiently. Now, as we come to an end, let's recap the key challenges that we discussed today. We asked the question, can we match expert distribution when the only thing you have are samples, right? You don't know the expert's distribution. The answer is yes, we can. We can do so by building an estimator to any f-divergence. Moreover, we showed that we can turn this into a game between a policy and a cost function. This game turned out to be an asymmetric penalty of the learner cost versus the expert cost. The follow-up question is, which divergence should we pick? We saw that if you pick forward KL, you run the risk of going off the expert policy. However, if you pick reverse KL, that problem's solved, but you need exponential number of samples. Key insight towards the end was what we actually care about is performance on any possible cost function the human may care about. That led us naturally to the definition of integral probability metrics, which are exact and linear and efficient. We end with an important practical question. What if some moments matter more than others? For a self-driving car, it matters more to avoid collision than breach boundary. Well, the framework can elegantly handle this by turning moment matching into a constrained optimization and having different slacks for different moments. It's just turned out to be different weighting for different moments in some sense, which makes moment matching a very powerful framework. And on that note, we are at an end. Thank you for your time. Be well, everyone.